Greetings, students. This is your BSB 102 Biology 2 online course, and today's discussion will be about the endocrine system. What is the endocrine system? It's a system of hormone-producing or endocrine glands. Right? All systems consist of organs, so an organ of the organ system, which we call endocrine system, is an endocrine gland. And on this slide you see all these different endocrine glands. You see underneath the brain of this person you see hypothalamus and the pituitary gland. These two regions or little glands below the brain stem are like headquarters of many other commanding center of the endocrine system. They control the work of other endocrine glands. For example, the pituitary gland produces hormones that stimulate the thyroid gland, hormones that stimulate growth of the body, hormones that stimulate production of milk in women who just had their babies, etc., etc. Many different functions are under the control of the pituitary gland, which is in turn under the control of the hypothalamus. You also see pineal gland, which actually it's a gland that takes part in the regulation of your sleep-wake periods, when it produces substances that can make you drowsy, sleepy, and substances that can wake you up. So it's like a biological clock in a way. And thyroid glands, we will talk about them in detail, and parathyroid glands. Thymus, also an endocrine gland, although usually it is discussed more in the lectures about the immunity because it controls the differentiation of lymphocytes into T lymphocytes. Then down below, underneath the liver and behind the stomach, the pancreas. Then on top of the kidney, adrenal glands, and we will talk about pancreas and adrenal glands in detail, and also glands that have to do with the reproductive system, which we will talk about in next lectures. So that's just a brief overview of what is the endocrine system. Now, what is a hormone? We say endocrine glands are organs of the endocrine system, and they produce hormone. Hormones are chemical messengers. So they are actually chemicals, they're molecules, which are produced by the endocrine glands. It says here they are used in the body by the endocrine system. They coordinate our organs. I would say better, look at this text box, it says hormones regulate metabolism, growth, and specific functions of our cells. For example, hormone called insulin, which you definitely heard about, it regulates the opening of the door for glucose in cellular membranes. Right? The hormone that is produced by, or a hormone produced by the endocrine adrenal glands may stimulate the production of glucose, or it may inhibit inflammation, etc., etc. So hormones regulate different specific particular functions of cells. Now, endocrine literally means gland, or endocrine gland means gland that produces something for inside. Endo is its Latin prefix that always implies something inside. There are other glands. There are organs that consist of cells which also produce something and secrete something, but they are not endocrine. These other glands are called exocrine glands, literally glands that produce something for the outside. A good example is sweat glands. They, they produce sweat. Sweat is not a hormone. It is not regulating any function, specific function of cells in the body. It is secreted on the surface of the skin and it evaporates, thus cooling the body. But it's not a hormone. It's not that it's produced by the endocrine gland. Now, how do hormones work? First and foremost, please remember this very important point. A hormone is secreted by a cell of an endocrine gland. You see it on the left in the picture. It's a secreting cell. It secretes the hormone into the blood, right? Into the bloodstream, into the circulation. That is into a nearby blood vessel, which is a capillary. Usually, cells contact with capillaries. They don't, well, most of them do not contact with large arteries or large veins. They contact with blood capillaries. The hormone is then carried by blood to all destinations in the body. So it's a long-range weapon. The pituitary gland is underneath the brain, so it's in the skull, but it produces hormones that circulate in the blood and can reach, for example, your toes and regulate the growth of your toes, right? Or the growth of the skin on the soles of your feet or something. So that it doesn't matter for a hormone how far is the cell that it regulates from the cell that secretes it, because it is carried by blood in all destinations. Then, as a hormone reaches a certain destination, it acts only on its particular target cell. See, the secreting cell in the picture secreted or dumped a hormone, shown as little blue circle, into a blood vessel. Then the hormone travels in the blood, and boom, it reaches a place where its specific target cell is. For example, for thyroid stimulating hormone, the target cell is a cell in the thyroid gland. Or for a parathyroid hormone, the target is a cell in tissues of bones. And it's maybe far from where the secreting cell is. And there are two things here. Particular target cell has a specific receptor that matches only this particular hormone. In this picture, target cells have some appendages on their surface. They are receptors, special molecules or collections of complexes of molecules. And in this picture, see, it has a depression which has this oval shape, and this little blue sphere, little blue ball, fits right in. Right? It can bind to the target cell's hormone specifically. Imagine that this blue cell would be of a rectangular shape, not the shape of a little blue ball, but a little blue rectangle. It would not fit into the receptor of this target cell, right? So, and similarly, if the hormone travels in the blood and there are some cells contacting the blood capillary which do not carry the specific receptor for the hormone will ignore them. Right? The thyroid stimulating hormone produced in the pituitary gland will travel in the blood. It will reach the tissue of the thyroid gland and bind to receptors expressed only on thyroid cells. If there are some other cells somewhere on its way to the thyroid gland, it will ignore them. They don't have a matching receptor, a specific receptor for this particular hormone. That's an important concept to understand. That's why hormones do not share responsibilities. In a way, in this, they remind you, they are similar in a way to antibodies. right, or receptors of immune cells, lymphocytes. Uh, they make themselves specific to a certain target cell. They don't share responsibility. A hormone that stimulates production of milk in the woman's mammary gland will not share responsibilities with the hormone that regulates blood sugar. They have different target cells and they match different receptors. So that's why they are different and they regulate different cellular activities. Now, it is to understand how hormones work, it makes sense to divide them into two large categories. Some hormones are water soluble and some are lipid soluble. And the left part of this picture shows you a water soluble hormone, little white ball. It reaches its receptor. See, there is a large blue thing which has a depression fitting the shape of this hormone. So it's a specific protein receptor for this little white hormone in plasma membrane, in membrane of a particular target cell. Now, you may ask, so why is it so necessary for hormone to bind to a particular receptor? Can it not just go inside the cell and do something? No, it cannot. It is water soluble. Remember, cellular membranes are mostly lipid, right? Phospholipids. They will not allow any water soluble substances to penetrate into cells. So the action of this water soluble hormone begins with binding to a receptor. Then you see the receptor, something happens to it when a hormone binds it, and it transmits the signal inside the cell to like a queue of different molecules which may play a role of enzymes or something else, but in any way the signal is like relayed to some place either in the cytoplasm or in the nucleus, and thus the water-soluble hormone can change some biochemical reactions in the cytoplasm, or it can regulate genes in the nucleus, stimulate their work or repress their work, etc. The right part shows you lipid-soluble hormone. Now, lipid-soluble hormone does not need any receptors, and protein receptors to lipid-soluble hormones do not exist. The lipid-soluble hormone can be dissolved in lipids which are in the plasma membrane, in the cellular membrane. So there's not a difficulty for this hormone, shown as a light-colored triangle, simply to cross the cellular membrane and now to find its receptor somewhere in the cytoplasm. And then the receptor in the cytoplasm, bound by this hormone, transducts the signal usually into the nucleus and through another receptor protein in the or the same, actually, it can translocate this protein in the cytoplasm, can translocate into the nucleus, or relay the signal to another substance that will translocate into the nucleus. And then in the nucleus, this substance regulates gene expression. It can stimulate the work of the gene. If you recall from Biology 1, remember, to produce a protein molecule, genes must be first transcribed, right? An RNA message must be made from these DNA parts or genes. And lipid-soluble hormones are famous for regulating the transcription of particular proteins. So they can stimulate the transcription. So without this lipid-soluble hormone, the gene is not working and there is no product of the gene. But in the presence of this hormone, the gene begins to transcribe itself. building, or actually using enzymes, of course, that transcribe it and build a message which is then translated into a protein product. So that's the difference. Again, all hormones have receptors, but water-soluble hormones have receptors on the membrane, right? They cannot go through the membrane. Lipid-soluble hormones have receptors in the cytoplasm and in the nucleus of the cell. And so they do not act on anything in the membrane or anything in the cytoplasm. They act directly on genes regulating their work. And thyroid and parathyroid hormones, we're kind of moving from top to bottom. So we briefly talked about hypothalamus and pituitary gland. We said that those are regulating the work of other endocrine glands. Now, these other glands. See, to the left, you see the thyroid gland, and it produces 3 hormones. One of them is called T3 on the left, another T4, and yet another calcitonin. We will talk about calcitonin a bit later, but now T3 and T4. Why these T? T comes from tyrosine. It's an amino acid. And in the cells of the thyroid gland, this amino acid reacts with iodine groups. And either 3 iodine groups join the molecule of tyronine, or 4 of tyrosine, or 4. So in the first case, there will be T3, in the second, T4. These are active hormones, right? They will enter blood capillaries, travel all over the body, and they are interesting in that we just said that hormones have particular target cells. For these hormones, actually all cells of the body are their target cells. And what they do, these T3 and T4, they stimulate the metabolism. So burning of organic molecules, large organic molecules, in the presence of T3 and T4 is accelerated, enhanced. Right? Then parathyroid hormone. I will say something before we go to parathyroid hormone. Thyroid hormones are, you see there is an arrow going from the pituitary gland to the thyroid gland, and it says TSH. TSH stands for thyroid stimulating hormone. So the work of the thyroid gland is under the control of the pituitary gland, and the pituitary gland in turn is under the control of hypothalamus, which you see there is an arrow saying TRH. It's thyroid releasing hormone. So it releases the production of thyroid stimulating hormone, which then finds its target cells in the thyroid gland, and in response, thyroid gland produces T3 and T4. The third hormone, calcitonin, it's not under the regulation of TSH, and it has a peculiar function which has more to do with the function of parathyroid hormones. Now, parathyroid hormones, you see, they are produced by something within the tissue of the thyroid gland. You look at the picture, the right part of the picture, you see 4 red spots in the tissue of the thyroid gland. The thyroid gland is, by the way, you probably know where your thyroid gland is, right? It's in front of your neck, right in front of the cartilage that forms the wall of the respiratory tract. And within the tissue of the thyroid gland, there are 4 little parathyroid glands. These yellow spots are parathyroid glands. They produce parathyroid hormone. What does it do? Parathyroid hormone regulates calcium exchange between blood and bones, making blood calcium higher and bones sturdy. Right? this parathyroid hormone targets certain cells in the tissue of bones, making them release calcium into the blood. So blood calcium goes up. And the response of the bone to this release of calcium is making more calcium in the form of inorganic, insoluble calcium salts. Right? So parathyroid hormone, we say, mineralizes bones, makes them sturdy. Bones are sturdy because there are insoluble calcium salts in them. In the case of the lack of parathyroid hormone, blood calcium is low, and bones are abnormally soft. Uh, Parathyroid hormone, it is shown here. There is a green arrow saying vitamin D, and it points to the intestine, but actually vitamin D points also to bones, just like parathyroid hormone. It has several kinds of target cells, but its function is basically the same as the function of parathyroid hormones. It increases the concentration of calcium in the blood. Then a couple of words about calcitonin, the third hormone of the thyroid gland, pictured in the left part of this picture, on the right from the thyroid gland, your right from the thyroid gland. This hormone counteracts parathyroid gland and vitamin D in that it lowers blood calcium. So it's like a homeostatic negative what feedback, right? There's a homeostatic feedback mechanism for the for keeping your calcium in the blood at a certain level. If it goes too high, calcitonin makes it lower. If it goes too low, then parathyroid hormone and vitamin D make it higher. In the presence of large amounts of calcium, relatively large amount of calcium, muscles work normally. In the conditions when calcium is low, muscles may respond by twitching. And this is actually a very nasty thing. In patients who underwent surgery on the thyroid gland, sometimes surgeons involuntary, just by technical mistake, they remove some part of the parathyroid glands, one of the four or one half of the four parathyroid glands, and this makes calcium low in the patient, and the patient experiences these sudden blood twitches, and it may be very bad, especially when a person is driving. Imagine muscle twitches begin, and this patient cannot really hold on to the steering wheel. So I personally know one a man who underwent the surgery on the thyroid gland, and one of his four parathyroid glands was removed accidentally. And till this date, it was like 20 something years ago, but to this very day, he takes pills that are like hormonal replacement therapy, synthetic parathyroid hormone. And he has a rule that he will never drive at night, especially in freeways, only at daytime. But at night, he says, it's too much of a risk for me and for other drivers, because if, God forbid, I have these twitches, I will make a terrible accident. During the daytime, it is still easier to control the wheel. Even if I have some twitches, I will control it. At night, I might lose the wheel for a split second, and because I don't see so clearly, I will hit some other car, and other cars will hit me, and it will be a disaster. So parathyroid hormone is very important. Again, it regulates the concentration of calcium. It keeps it relatively high. If it overworks, then calcitonin puts the calcium concentration down. Okay, and about a couple of words about bones. We say parathyroid hormone and or vitamin D makes blood calcium high, and it makes bones sturdy. If there is not enough of these hormones, especially vitamin D, bones become soft, abnormally soft. There is a pediatric condition called rickets. Rickets, it's the condition when bones in small kids do not harden. And when kids begin to walk, the bones of their legs become curved. Right? And, then later, this kid grows up, and the shape of legs remains kind of not straight, and it is noticeable. So it's very important that children, especially small children, infants and toddlers, receive enough vitamin D. Vitamin D production is stimulated by sunlight. If small kids do not receive enough sunlight, their bones suffer. So if they live somewhere like far north, in northern Alaska, or somewhere near the North Pole in northern Norway, or Svalbard Islands, they're very close to the North Pole. In winter, there is no sun. Polar night. It's totally dark for like 3, 4, 4.5 months. There is no sun. There's no daylight, and in this case, the kids have to be artificially they must receive something that replaces this natural sunlight, and the best way to do it is just put dark goggles on them and place them under a strong ultraviolet bulb. They get enough ultraviolet radiation that stimulates their production of vitamin D, and it's good for their bones. Also, in grocery stores, there is this vitamin D fortified milk. It's a wonderful product, and it should be given to children, especially again to those children who suffer from the lack of enough daylight. Okay. Now, consequences of low and high thyroid hormone production. We talked about consequences of low parathyroid. Now, low thyroid on the left. It may be that you know some people who have hypothyroidism, or low production of thyroid hormones. The function of thyroid hormones T3 and T4 is to stimulate metabolism. So in people with low T3 and T4, metabolism is slow, which means that they do not burn enough fat, they do not burn enough complex carbohydrates like glycogen, and it shows they gain weight. Then, because of the slowed down metabolism, their body temperature goes down. Right? Not enough energy to maintain the heat of the body. They become slow in their perception, attention, reactions to changes in the environment, etc. So generally slow, and they are very somnolent. They want to sleep all the time, all the time, all the time. Now, sometimes people make fun of them and say, you probably eat too much. That's why you are so big, and your weight goes up. And it's very unfair because some patients with hypothyroidism actually eat very little. They try to, they themselves are afraid to gain weight, and then they put themselves on low-calorie diet, and still they gain weight, because it's not because of the of what they eat. It's because how their cellular metabolism works. If it is slow, then even if they eat little, they gain weight. And on the left picture, on the right side of the left picture, you see the same woman, which is pictured with hypothyroidism, after treatment. And the treatment can be of two kinds. One, some people have this hypothyroidism simply because they lack iodine. I mentioned, your textbook mentions that to become active thyroid hormone, the amino acid thyrine must be joined by iodine groups. If the diet has no iodine, if the water that people drink has no iodine, there will be hypothyroidism. You know who has a risk of getting this kind of hypothyroidism? People who live high in the mountains, because the higher you go, the less iodine is in water. And so they suffer. It may be endemic, like a whole village somewhere high in the mountains shows symptoms of hypothyroidism because their source of water lacks iodine. And in this case, the treatment is very simple. Just give these people products that have the iodine, like iodine-rich salt. It's sold in the grocery stores. So it's not very difficult. There might be another kind of hypothyroidism when the T3 and T4 are low, not because there is no iodine, but because simply there is something wrong in the cells that produce thyrine. And so that's the reason of hypothyroidism. In this case, it's a little bit more complicated. The treatment may be longer and it may be somewhat more expensive because this person needs artificial synthesized T3 and T4. And in some cases, it is done and it helps. Now, in the picture on the right, hyperthyroidism. Again, you might have encountered people with this hyperthyroidism, or thyroiditis, or Graves' disease. I mentioned it in the lecture about the immune system because it is an autoimmune disease, an autoimmune disease. It makes the cells of the immune system produce antibodies which imitate or mimic the thyroid stimulating hormone. So they stimulate the production of T3 and T4 all the time. And people with hyperthyroidism have too much of these hormones. So their metabolism is sky high. It's very high. They burn every food that they eat right away. They can develop a wolf's appetite. They're always hungry. They may impress, during a party. They can eat a lot, and people look at them and say, wow, this young woman or this young man, they're so thin. They eat so much. They stuff themselves with food and they don't gain weight. Lucky, lucky people. Not really, because in addition to low weight, people with hyperthyroidism have high body temperature. They have bulging of the eyes because excess of T3 and T4 acts on certain muscles that regulate the bulging of the eyes, and their eyes become sort of like bulging, and they like stare at you all the time, and sometimes people get frightened. And also they have increased reactions to the environment. They are very sharp, they're very fast, but they cannot concentrate, right? So they, just like people with hypothyroidism, may get behind in classes because they are slow, they cannot study, they feel so sleepy all the time. In people with hyperthyroidism, it's the opposite. They feel very alert, but they cannot concentrate. They read fast, and they read a lot, and then they forget everything that they have read. And so, again, they can get into trouble in their classes. They cannot keep up with the class. And the therapy in hyperthyroidism, again, it's rather simple. either surgery, right? A surgeon can just remove part of the thyroid gland and symptoms usually go away. Or it can be even without surgery, a very good replacement of the surgeon's knife is a radioactive isotope, radioactive iodine. An injection of radioactive iodine, iodine 131, is followed by this radioactive iodine incorporating into the tissue of the gland and working exactly like the surgeon's knife. Iodine 131 is an active gamma emitter. It emits gamma particles which simply destroy cells, destroy the tissue around this place where radioactive iodine has incorporated. So it's like surgery. I can share with you my, again, personal history. My grandfather had a pretty bad case of hyperthyroidism when I was very little. I barely remember him, but I kind of remember him being very thin. And then he got treatment with radioactive iodine, and it helped. He had some symptoms of hyperthyroidism even in later years when he was getting really old, and so I remember him very well. He was not really absolutely abnormally thin, but he was on the thin side, and he was sleepless. He was one of these sleepless people. He tried to get some medications, and these medications never really helped. So he just stayed very late at night and kept reading. And then he would tell you a story about the book that he thought that he read, but it would be very confusing because he actually forgot the content of books that he read. He couldn't concentrate his attention on the plot of the book, and it would all kind of get mixed up in his head. So he would tell fantastic stories about books that he read. So that's hyperthyroidism. Remember, both hypo and hyperthyroidism are frequent. They are not rarity. You can have friends with these conditions, and so know how to talk with them. If they ask you, what should I do, then tell them what you learned from this lecture. Now, adrenal glands, the glands that can stress you out, but also heal your rashes. I invented this title. Thing is, that adrenal gland shown on top of the kidney at the left, on the left part of this picture, produces adrenal hormones. The adrenal hormones are of two different kinds, because, like your book mentions it, that each adrenal gland is like a fusion of two glands. One is shown in the picture in the middle as the lower level, the floor of this section of the gland. This floor produces adrenaline. Right? Adrenaline is a stress hormone. It makes your heart work harder. It makes your bronchi dilate, allow more air to go into your lungs. It raises your blood pressure. It suppresses your digestive system. So, for example, salivary glands are paralyzed, and your mouth becomes dry. And it's a rather common symptom of stress when you are afraid of something, frightened by something, like an evil-looking barking dog. Then you may get so stressed that your mouth becomes dry. It's pretty common. But there is another portion of this gland in the picture in the middle. It is shown as the middle zone, the middle part, and the upper part of the section of the gland. They're called cortical hormones, corticoid hormones. from the word cortex, which means the outer part, like cortex of the adrenal gland. They have many different functions. One of these hormones produced by the upper portion cortex of the adrenal gland regulates the volume of circulating blood. Right? So when people bleed, then this hormone stimulates retention of water in the blood capillaries and in the entire circulation, and so the volume of the blood is restored. So it's a very important, useful hormone, which, and unfortunately, in many of us, it is produced in excess. So we have bigger volume of circulating blood, bigger than we need, and it creates higher blood pressure. And also, importantly, the corticoid hormones are anti-inflammatory. Right? It's a very interesting feature. If you remember, you might have encountered this name, Selye. Hans Selye was a scientist who we actually owe him for the word stress. He was the first who introduced this word stress, stress-related conditions, etc. And Selye showed that when experimental animals are stressed out, when you bother them with something that makes them frightened or stressed out, then their cortex of their adrenal gland becomes hyper. There's a hypertrophy of the cortex. It becomes bigger than it normally should be, and they have a huge concentrations of corticoid hormones that, just like adrenaline, they can even enhance the stress, and they are actually partially responsible for the stress. But also, these hormones can heal wounds. They can slow down inflammation. They can suppress generally the immune system. Remember, glucocorticoids, the treatment that is given to patients with autoimmune diseases. So corticoid hormones suppress immunity, and it may have different meanings. Like if you're constantly stressed and you have this constantly high level of corticoid hormones, then your immunity is poor and you succumb to infections. But if a patient with, say, lupus has this huge reaction of her, usually it's her, rarely his, own immune system against her own kidneys, and she develops lupus nephritis and blood and kidney failure, then glucocorticoid hormones can save her life, actually, and prolong her life. A little bit of what can go wrong with adrenal glands. First, the picture on the left shows you the condition when adrenal glands do not produce enough steroid hormones. By the way, why steroid? The corticoid hormones are lipids. Chemically, they are lipids, and they're lipid soluble, and their chemical structure is similar to steroid hormones produced in the sexual organs, in the testis of men and in the ovary of women. So they chemically belong to the same group, although they have a function which is different from sexual hormones. In people who have a lack of these corticoid, adrenal corticoid, or steroid hormones, the condition that develops is called Addison's disease, and it manifests as just general weakness. The muscles do not grow very well. People try to stay active, they exercise, and they still don't have this sculptured mass, of muscles. it's a hard life, and they easily succumb to infections. They cannot handle stress very well, and also they have a number of reactions of the internal organs which are listed here. You don't really have to remember uh, them. One interesting feature which I really want you to remember and know, in people with Addison disease, there is a vitiligo, or they have skin that looks like they just came from Hawaii and sunbathed all day long. They are naturally tan. Well, it's actually not correct to call it natural because it is disease-based. But it is getting tan without sunbathing or without getting irradiated by ultraviolet bulb. It's because if their corticoid hormones are not present in the sufficient concentration, then there is the so-called melanin stimulating hormone, which stimulates skin cells that produce melanin, the dark pigment. And melanin kind of takes over. It replaces the lacking steroid hormones and acts on cells of the skin, epidermis, upper layer of the skin, making the skin tan. In old times, Addison disease was also called bronze diabetes, but I think it's, first of all, it has nothing to do with diabetes, and then this name is kind of obsolete, it's historical. The opposite, patients who have elevated steroid hormones, corticoid hormones that are steroid hormones, they have the so-called Cushing syndrome, pictured on the right. And they, well, you can figure out that, well, if their adrenal cortex produces too much of these stress hormones, then they are stressed all the time. Well, yes, but it's not the most obvious consequence of having high steroid hormones. A more obvious consequence is deposition of fat in the body, and it is kind of strange. This patient is female, and she's shown with a large abdomen, but actually many patients with Cushing syndrome may not have this bulging big abdomen because they deposit fat in the upper parts of the body, face, neck, shoulders, upper back. That's where the fat develops, and so they have this swollen face. They have huge neck, like neck of a really obese person. Women may have very big breasts. And on the other, huge shoulders, reminding of shoulders of someone who is really into sports, like swimming or something, or tennis. But in fact, it's not really muscle; it's fat deposition in the shoulders. And then look at this person's forearms, hands, and legs. And sometimes it's amazing. The people with Cushing syndrome have very delicate, thin forearms and very delicate, thin, gracious legs. And then in combination with this huge swollen face, swollen fatty neck, a mountain of fat in the shoulders and the upper part of the body, and this very disproportionate. And let me tell you this: for the Cushing syndrome may develop because the adrenal cortex works too hard, but it also can develop if people receive glucocorticoids as therapy. That's a very nasty, unpleasant side effect of long-term hormone therapy when people receive glucocorticoids for a long time in large doses. But imagine a woman who has, again, the severe lupus, and her kidney is all but gone, and she's going into kidney failure. You don't give her enough glucocorticoids, she will simply die. Give her enough, and enough in this case means a lot, of glucocorticoids over several months intravenously. She will live. She will live. Her other kidney will take over, or the parts of the kidney that is partially destroyed will take over, and she will not go into total kidney failure, and that prolongs her life. Yes, she will look kind of weird, but you choose between life and death here. So glucocorticoid hormones are still prescribed in large doses to people with autoimmune diseases. The endocrine pancreas, very important part of this lecture. The pancreas is a gland, shown yellow in this picture. And it is located behind the stomach, and its part, on this picture, it's the left part of the pancreas, contacts the duodenum, that's the beginning of the small intestine. And pancreas has ducts which open into the small intestine. The large part, some say 90%, some say 99% even, of all cells in the pancreas are exocrine cells. Right? So they're little exocrine glands. Why we call them that? Because they produce digestive enzymes. Remember, trypsin, amylases, lipases, special lipases are produced exclusively in the pancreas. That product, imagine a digestive enzyme, it does not circulate in blood. Why would it, right? Just imagine that your blood is filled with trypsin. That's crazy. Instead, normally these enzymes are secreted outside into the cavity of the duodenum, right? So outside of the internal organs, outside of the circulation. Right? Trypsin never goes into blood capillaries. That's why the majority of cells of the pancreas are exocrine pancreas. But look at these little squares which are shown here. There is one square, very tiny square, little square, near the right end of the pancreas, and there is a larger square to the left of it. And look, how are they called? Pancreatic islets, like very small isles. These islets are actually groups, large accumulations, aggregations of endocrine cells. There are two kinds of them, of these cells. One, they're shown in the insert. One is called alpha cells. One kind is called alpha cells. The other kind is called beta cells. Both are endocrine. You see, this insert shows you exocrine acinus. It's exocrine cells outside of the isle. Inside the pancreatic islet, there are only endocrine cells, alpha and beta. And what is their function? The alpha cells produce a hormone, true hormone, circulates in blood, called glucagon. And the beta cells produce, again, hormone, true hormone, circulates in blood, hormone called insulin. Insulin, both are very important, and I'll tell you in advance, we will see this in the next slides, but I'll tell you, these two hormones are the hormones that regulate your blood sugar, and you need to know how. If you finish this course and before you started it, you knew that insulin regulates blood sugar, and after you finish this course, also, again, all you know is that insulin regulates blood sugar. That's not enough. I want you to know exactly what insulin does. We'll see it in the next slide. One funny recollection about this word islets. I remember a student who, it was a guy, and in his final exam, he wrote whenever there was any question about the endocrine pancreas, he wrote eyelids, like Eyelids, eyelids, like eyelids on your eyes, and he wrote pancreatic eyelids. I was very surprised. I asked him why. Where did you get this? Your book never mentions any eyelids in the pancreas. And he says, I got it from your lecture. That's what you told me. I have a note. I have notes from you. So I figured that this guy heard eyelids, and he never bothered to check with the textbook and just wrote down eyelids, and it didn't seem strange to him that there are eyelids in the pancreas. So please read your textbook. You know, your ears may deceive you. My accent may deceive you. My Eastern European accent may deceive you. So please always supplement your work on these lectures by carefully studying your textbook. Now, how does insulin work? Exactly, that's what I want you to really know. See, the picture shows you a cell, and it may be, insulin targets many types of cells. The number one target cell for insulin is cell of the liver, but it also targets cells of the intestine, it targets cells of the muscle, neurons of the nervous system are also targeted by insulin. Skin cells, a very broad spectrum of cells are targeted by insulin, and they are targeted because they have this insulin receptor. You see on the upper left corner, insulin is shown like a UFO sort of landing, right? And on the cell there is a blue place for the land reserved for the landing of this UFO insulin, and it is called insulin receptor. So when insulin is produced and when it binds its receptor, what happens? The picture, again, the left half of this picture shows you a green landing place near the blue landing place. The blue landing place is a receptor for insulin. The green landing place is actually not for landing. It is a channel which allows glucose to go inside the cell. So glucose is water soluble. It cannot be dissolved in lipids, so it cannot cross cellular membranes. If this channel for glucose, simply empty space, if it is closed, if there is some door, some gate that is locked, there will be no influx of glucose into the cells. Glucose will remain in the cytoplasm. But look what happens normally, shown in the right half of this picture. The insulin has landed, right? And when that happens, the channel for the glucose is open. You see there is an empty space, and these little balls that symbolize glucose go one by one from the outside inside the cell, right? And that's where they are needed. Glucose is needed by the cells. It is, remember, it's a number one nutrient, right? It undergoes glycolysis, and then this pyruvate produced by glycolysis is used in the tricarbonic or citric acid cycle, right? And the energy from these reactions powers the synthesis of ATP. So no glucose, very little or no ATP. Now, it is not shown on this picture, but you need to know that while insulin decreases blood glucose, see, because it opens these channels, glucose goes in, or in other words, it goes out from the blood. So blood becomes glucose poor. Glucagon does the opposite. It increases blood glucose. The reason is that it increases blood glucose. It's not. It acts independently of insulin. Actually, it doesn't act through the insulin receptor, and it doesn't do anything to glucose channels. Instead, it targets its own receptors on liver cells, and this stimulates release of glucose from liver cells. More specifically, you may or may not remember it, but chemically speaking, a glucagon stimulates the breakdown of glycogen. Liver cells are very rich in glycogen, and the pinching off of individual residues of glucose from the glycogen molecule and releasing them into the blood. So again, homeostatic feedback. When your glucose is high, right, imagine that you ate 3 donuts. Please don't eat it, just for the, don't do it, but just for the illustration purposes. You ate 3 donuts. Your blood glucose went from normal 100 milligrams per deciliter to 700 milligrams per deciliter. Then the response to that is production of insulin. Insulin will bind its receptor, open glucose channels, glucose will go from the blood into cells. Now, if that, for some reason, goes out of hand, if glucose becomes so low in the blood that your tissues feel it, then homeostatic negative feedback. The production of insulin goes down and the production of glucagon goes up. And glucagon increases the release of glucose from liver cells and kind of returns the system to the, how do they call it, well, stable level, homeostasis, right? Please, you don't have to remember it. I make my human physiology students to remember it because I think for pre-nursing majors especially, it's very important to have this figure in your head rather than looking for, go to books, references to find what exactly is the normal level of glucose. 70 to 110 milligrams of glucose per deciliter. In the classical American, actually it's Old English, system of measurement, it's 0.02 to 0.04 ounces of glucose per 3.4 fluid ounces of blood. Or if I can make it even more like visually more user-friendly for you. 1 milligram is approximately 1/10 of a spoon. Right? So 10 milligrams is a spoon. 7 spoons is 70 milligrams. And these 7 spoons of glucose are dissolved in 100 milliliters or deciliter, 1/10 of a liter of your blood. That's normal amount of glucose. Deciliter or 100 milliliters, it's like a glass, a standard glass of something. So 7 spoons of glucose per oh no, sorry, milligram is probably not 1/7, not 1/10. It's it is 1/10,000th, right? Because it's milligram. 1 gram is one fifth. So it's less than that. It's not 7 spoons. It's like 0.7 spoons or something. This is a pretty small amount of glucose, if you imagine. I myself remember it from almost from childhood, from adolescent years, that 70 to 110 milligrams of glucose. Some old doctors would say, well, 80 to 120 milligrams is okay. But recent convention is that it's 70 to 110. If your glucose level is lower than 70 per 100 milligrams per 100 milliliters, It's called hypoglycemia. You feel it. Right? It manifests as weakness, cold sweat, especially hands and feet are covered with cold sweat, trembling of the hands, shaking of the hands, shaking feeling of trembling in the legs, and in sudden increase in appetite. People with hypoglycemia say that they feel this sudden uh, burst of appetite when they want to eat something real big. It's such a sense of hunger. And it may lead to actually loss of conscience and coma. So severe hypoglycemia must be treated, and the treatment, of course, is glucagon. Glucagon raises blood glucose. In less severe cases, it is enough to eat, give this patient something to eat. And best of all, it's a piece of cake or a glass of fruit juice with high sugar in it, like in American grocery stores, basically all so-called fruit drinks are laden with sugar. So a glass of regular orange juice sometimes does the trick. Then the glucose goes up, when it is higher than 1 milligrams per deciliter, then a condition is developed which is known as sugar diabetes, right? Or diabetes mellitus. Mellitus means sugar diabetes. Sweet diabetes in Greek. Mellitus means sweet. Uh, all types of, there are three types of diabetes, but all three of them are about the rise of glucose in the blood. You see in the upper right corner, there is this arrow pointing up. And it's like the blood sugar grows exponentially, not linearly, but like very fast, like exponent. Uh, what is the reason of this high blood glucose? In type 1 diabetes, it is simply lack of insulin. Right? It says here in the insert, it is due to the body's malfunction to produce insulin in the body, and it requires the person to inject insulin or somebody else to inject insulin. Then type 2 diabetes. It's when insulin is produced, sometimes even in large amounts, larger than necessary. But still, glucose remains high in the blood and low in cells because cells resist insulin. You saw in the previous slide that normally when insulin binds to its receptor, cells open their their glucose channels. And in people with type 2 diabetes, it doesn't happen. Cells resist. They keep their glucose channels closed. Right? So again, high glucose in the blood, low glucose in the cells. And finally, there is a rather rare, not very frequent form of diabetes, type 3, or gestational diabetes. It's a condition that is characteristic for some pregnant women during gestation and during the growth of the uh, embryo and fetus. And usually it's not really an independent disease. Like type 1 and type 2, they are different diseases actually. They are because of different reasons. In type 3 diabetes is usually just kind of like aggravation or um, uh, sudden manifestation of previously undiagnosed diabetes. When a woman didn't know that she had diabetes, but when she's growing her embryo in her womb, she suddenly gets high glucose. That's gestational diabetes. Uh, Now, why is it so bad to have diabetes? And these pictures and this text actually explains you why. First of all, regardless of the type of diabetes, glucose in diabetics remains in the blood and does not reach cells. This causes death of cells by starvation. Right? Cells starve. It's like there's plenty of glucose outside, but there is no glucose in the cells, right? Or very little glucose in the cells. Many cells cannot stand it. Some can, but there are some especially vulnerable cells. Cells on the cover of the soles, the epidermis of the sole, of the feet. They are, of course, they're vulnerable. They are always under pressure. When you walk, you make them really squeeze. And so when, in addition to that, there is no glucose, they simply die. Also, retina of the eye. It's one of the early manifestations of diabetes is changes in the retina of the eye. You yourself cannot see that. It's a doctor, ophthalmologist, or optometrist can detect changes in the retina. They have special equipment for that. And the reason for that is that the neurons, cells of the nervous system, which are very abundant in the retina, again, they are extremely sensitive to a lack of glucose, and they begin to die in large numbers, which may cause blindness if not treated. So, death of cells, death by starvation. Another scenario, actually, it happens, all these processes go together. I would probably say not the alternative scenario, but additional scenario. In the absence of glucose, the cells burn lipids, right? Burning proteins, that's like the worst case scenario. But burning lipids, it does happen when there is not enough glucose in cells. And again, it can be a late symptom of diabetes, but it can also, diabetes can begin with this. It can be an opening symptom, a start of the disease. When cells suffer from the lack of glucose, and they have to get energy from somewhere, right? So they split their lipid molecules, right, and use the energy of the broken chemical bonds for synthesis of ATP. It is possible, but breaking molecules of fat means release of free fatty acids. And fatty acids are acids, right? So they make the internal environment of the body acidic. And in addition, some of these released fatty acids undergo a chemical conversion into substances that are kind of like acetone, nail polish remover, peculiar smell, right? So the condition is called ketoacidosis. Keto from ketones, acetone is a ketone, and acidosis because the environment gets acidic. It is a very grave condition when ketoacidosis goes unchecked, untreated. The person loses conscience. The person becomes comatose, right? And unless you give this person insulin, or if it is a type 2 diabetic, then be careful, don't give insulin. Give some medication that decreases the insulin resistance. There are some available. So without medication, if ketoacidosis continues, it's lethal. One age-old and very simple diagnostic sign of ketoacidosis, when you walk down the street and see someone suddenly falling down. And, well, sometimes people think, that's a drunk, I will not help that person, why would I? He shouldn't drink so much. But actually, if you approach the nostrils or the lips of this person, you will feel this peculiar odor, scent of acetone, nail polish remover. In this case, it's almost like we say in medical people have say pathognomonic symptom of ketoacidosis, the unique symptom of diabetic coma, and this person, it's not just drunk who will lie down for a while, sleep, and then wake up and go. This person must be brought to a hospital and treated seriously from diabetes. Also, diabetics can develop impaired kidneys. Uh, and again, this malfunction of kidneys may be the first symptom of diabetes. The thing is that when glucose is so high in blood, it becomes also high in kidney tubules, and it results in the influx of water into the urine that is forming in the kidney. We'll talk about it in the next lecture. So the amount of urine, normally a person urinates several times a day, and the total volume is about 1 liter, not more than 2 liters, like 1/4 of a gallon, or not more than 1/2 of a gallon per day. But diabetics sometimes release 5, 6, 10 liters of urine per day, and they go to the bathroom very frequently, and it bothers them at night. They have to wake up like 5, 6 times a night and go and urinate. And of course, this leads to dehydration. Water is lost from the body, and the sensation of thirst. Sensation of thirst is, it may seem like it's not a big deal, drink some water and will go away, but in diabetics it may be so bad that it really tortures them, it torments them, it is constant thirst. So living with diabetes means suffering from a serious disease, regardless of the type 1 or type 2. And finally, one kind of concluding thing. Type 1 and type 2 diabetes, different origins, different treatment. Type 1 diabetes is never a patient's fault, shown on the left part of the picture. It is an autoimmune disease where, for no known reasons, certainly not because the patient did something wrong, the immune system destroys the insulin-producing beta cells in the patient's pancreas. Type 1 diabetes can be treated by regular injections of insulin. Right now, there are some basic science labs that are working on the idea of gene delivery. It is probably the future of treatment of type 1 diabetes when, beta cells are gone, but you can insert the working gene that produces insulin into other cells of the pancreas, right? And this is something that scientists are trying to work on, but it's not today's medicine. Today's treatment for type 1 is simply injections of insulin. Now, the modern equipment, thank God for modern plastic syringes and modern needles, especially, that can be made very sharp and thin. So the injections of insulin, they are subcutaneous, simply under the skin, not in the muscle, not into the vein, but simply under the skin. They can be done by the patient himself or herself, and I know people who do it to themselves, and they say it's not a big deal, it's really not painful. The thing is simply to remember and not to skip these injections. If you skip injections, you may go into ketoacidosis. And on the other hand, if you overdose insulin, that's also bad, because hypoglycemia is very bad too, not just hyperglycemia. Hyperglycemia will lead to diabetic coma, but hypoglycemia may cause the so-called insulin coma or hypoglycemic coma. And in this case, drinking orange juice will not help. The patient needs to be injected with glucagon, and modern kits that contain syringes with insulin for diabetics. They also contain a couple of syringes with glucagon, just in case. What if the patient overdoses the insulin, then an injection of glucagon will come in handy. And of course, the rule here is monitor your blood glucose. There are wonderful monitors that do not really, all of them need a little blood, but there are some monitors that can tell you how much glucose your blood has if you just prick your finger with a tiny lancet or needle, and just a tiny drop, one tiny drop of blood is enough for the modern it's actually a photometer. Photometer will tell you how much glucose is there. Now, type 2 diabetes on the right part of this figure. Type 1 diabetes is never a patient's fault. Type 2 diabetes is always the patient's or the parent's fault. Nowadays, more and more kids have type 2 diabetes, so it's definitely their parents' fault, guardian's fault, school's fault, whatever, whoever supervises these kids and their nutrition. Patients with type 2 diabetes have enough or often more than enough insulin. And so injections of insulin will never help type 2 diabetics. It will be without any effect or bad for them. Right? Increased insulin when it is already high will be pretty bad. But the thing is that the cells resist insulin. They do not open their membrane glucose channels in response to insulin. And the case of this type of diabetes, type 2 diabetes, is obesity. Obesity, obesity, obesity. When body fat is accumulated, each pound of extra body fat increases insulin resistance. It's strict, data. It's not somebody's fantasy about how to look slim and lose weight, be on some cruel diet because you want to look good. No, in this case, it's not about looking good. It's about really, living more years and stop suffering from this frequent urination and cell death and comas of different kind. So what is the treatment in this case? First and foremost, diet. Diet. People with diabetes type 2 have to lose weight. It's the matter of life and death. And it may be very difficult, especially in older patients, it may be difficult. In kids, it should not be that difficult, but if parents do not know about type 2 diabetes, if they do not pay attention how their kid eats and what their kid eats, and their kid eats only junk food because mom does not cook, and buying takeout food in good restaurants is expensive. So what to do? McDonald's, Burger King, whatever. It's very bad. The junk food is always laden with fat and always laden with complex carbohydrates. French fries, it's like the worst kind of food for type 2 diabetics. It's lethal for them actually to gorge on French fries because you know how French fries are prepared. They're actually boiled in molten oil, right? So they're very fatty, and hamburgers, of course, are very fatty. And these hamburger buns, they're not fatty, but they contain a lot of starch and glycogen. So it all increases the weight rather than decreases it. So diet is absolutely important. Um, uh, okay, and also physical exercise. I wanted to put this slide here, and I don't have it. I lost it. I used to have it. When a mom tells a child, go out and play. You're sitting at your computer indoors all day playing these video games. You have to go outside and play. And the child goes outside, brings a chair, puts it near the window. Right, the computer with video games is behind the window, and the kid puts the ear plugs or these ear piece on his ears and continues to sit and play video games all day. So it's not physical exercise. It's not really outdoors. Kids must run. Kids must swim. Kids must row boats, ride bicycles, be exposed to plenty of fresh air and strain muscles, make your muscles contract. This is a wonderful way of keeping your weight within the normal range. So diet and exercise, they are most important for children. Uh, as I already have confessed to you, I am not the best person when you talk about keeping healthy diet. I know that I overeat sometimes, and I am a bit overweight. I'm not obese yet, but I know I'm under danger to become obese. If my body mass exceeds 30, then I will be fat, and I'll be obese. And I'm really trying not to do that. But I'm not a diabetic. My blood glucose is usually like 90, 100, rarely 110. Uh, if I did not eat before, if it's a fasting glucose. So I'm within normal range, but I remember about it, and I really try hard not to indulge in sugar. I don't eat French fries from McDonald's, really, guys. It's a taboo. It must be a taboo. It must be something that you should not eat, and especially your children should not eat. When you travel, sometimes go to McDonald's and just tame your hunger. But on a regular basis, eating McDonald's food and stuffing your kid with McDonald's food, please don't do it. Please don't do it. Okay, that's pretty much it for this lecture. Next time, the uh, 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 kidneys, right, the urinary system, and remember that we are approaching spring break, and you will have your exam during the first week after the spring break, so please do not forget to register. You can start registering even, well, not now because I haven't published the questions of the exam, but I will do it very soon. So uh, remember about registering. I don't want it to happen in the last moment, and I will let you know. I'll put an announcement on the Canvas that exam questions are published, and you will have at least one more quiz on the immune system and on the endocrine system, and maybe also I think also on the uh, urinary system. It can be one large quiz or a couple of smaller quizzes, but I must check your uh, how you follow these lectures before the exam. Okay, see you soon during the next lecture.